So in terms of generation and measurement of high voltages, we have discussed how to generate high voltages. We've also discussed in brief how to measure high voltages, what are the different kinds of equipment we use so that we are able to measure the high voltages that we work with in the laboratory and in the field. Now, one of the most important aspects of high voltage measurements is in insulation assessment. We need to assess the condition of the insulation, and therefore we have a large number of techniques which are used in order to measure certain properties or certain characteristics of the insulation in question. So in this lecture, we are going to talk about insulation assessment and discuss some methods which are currently in use for assessment of insulation condition. These will cover various measurement techniques, and of course we have already covered one of the most principal measurement techniques, and that is partial discharge measurement. One of the most important aspects of condition monitoring is when we measure properties like breakdown strength or time to breakdown. These are all destructive tests, and therefore they can only be done economically. I mean, they cannot be done in a widespread manner. They are destructive tests, and they have to be done with caution. So therefore, we need a large number of non-destructive tests which can predict failure or which can predict aging of the insulation. As I have already discussed, partial discharge measurements or partial discharge diagnosis is one of the most important tools we have in condition assessment, insulation assessment. In this lecture, we are going to discuss some other techniques. So as I said, there are broadly three different ways of assessing insulation. One is, of course, the overvoltage withstand test. As an insulation deteriorates and degrades over time, the dielectric breakdown strength of the material will deteriorate, and therefore it will lose its capability of withstanding high overvoltages. But then again, we are talking here of destructive test, and this is not always useful. However, we have talked about overvoltage withstand test and how to go about that. In this lecture, we will talk about non-destructive electrical measurements. Again, we have already talked about PD measurements, electrical PD measurements. We are going to talk about other methods. Then, of course, we have physical and chemical determination that may require access to the sample of the insulating material. Some of these methods we have already discussed when we have discussed PD. Apart from physical and chemical techniques for PD detection, there are also certain other methods which are physical or chemical in nature and which are used to assess the condition of the insulation other than PD diagnosis. So these are the number 2 and number 3. These are the two things that we'll discuss in this lecture. So let us here look at non-destructive electrical measurements. The most important or the principal non-destructive electrical measurement for condition assessment of an insulation that we can think of is the insulation resistance measurement. What does insulation resistance measurement involve? IR measurements, as you can make out from the name itself, measures the resistance of a dielectric or an insulation structure. So we may not be looking at a particular sample of insulation, but rather the entire insulation system as a whole, and we want to measure the resistance of this insulation system when a high value direct voltage is applied. So this is the this is the DC resistance that we are trying to measure. In principle, so for the principal tool that we have for measurement of insulation resistance is the Megger, and the principle of Megger circuit is shown here. Essentially what you have is you have a hand-driven motor, or either a hand-driven, manually driven, or a motor-driven DC generator. So this is the DC generator that you have. This can generate high voltages up to even 5 kV. You have a current coil which is shown by this coil 1, and then you have a voltage coil. Now, when this circuit is energized, there is a current coil is energized as well as the voltage coil is energized, and as a result, these coils experience torques, and the torque that is experienced by the current coil and the torque that is experienced by the voltage coil are designed to act in opposite directions, so that the ultimate deflection of the needle, this ultimate deflection of the needle, is due to the interaction between the current coil and the voltage coil, and this will be a measure of the ratio of the voltage to current. So on this scale, what you will measure is the ratio of voltage to current, which is your resistance. Remember, the scale in this case will be non-uniform, and you will have a bigger scale, a more spread out, wider scale in the high resistance region. It will be more cramped in the low resistance region. So this is the principle of the Megger operation. Now, if you look at the currents that you expect to flow through the insulation, you will have currents, and from the currents you will estimate the resistance. Now, if the current, even though it is a DC voltage, the voltage is constant, the current will not be constant, because there are various kinds of currents that are operational in a insulation. The total current that you will see is given by the plot 1. This is given in terms of a magnitude versus time. So as you can see, initially this is the current that we are looking at from time scales of 1 seconds to 10 seconds. Initially, the current is very high, and then the current goes down and ultimately settles at a much lower value. Now, if this is the total current, this can be considered to be composed of several components, 2, 3, and 4. What are these components? The first component is the absorption current. This is the current that flows because you are working with a dielectric material, and the dielectric material is polarizable. So when you energize this dielectric current, there will be a current flowing through the dielectric, which will cause the material to polarize. And once polarization is complete, this current will die out. I will discuss polarization currents in greater detail a little later in the lecture, but let us just work with the idea that this current too denotes the absorption current, which is high at the beginning and ultimately goes down to a very small value. In fact, ultimately, given sufficient time, it should go down to 0, but that may not happen in very short times. Then you have the conduction or the leakage current, that is given by curve number 3, which is the typical ohmic current or conduction current that will flow in a material on application of DC voltage. If you did not have a dielectric material, this current would still flow. This current originally may be small, and then the current increases and ultimately reaches a steady value. So as long as the voltage remains applied, a steady DC current will flow at long periods of time. The current will go to 0 as soon as the DC voltage is removed. And lastly, we have the capacitance charging current. You have a dielectric material, therefore this dielectric material behaves like a capacitor. It can store charge across it. It can store electrostatic energy. So the capacitance, the capacitive charging current that will flow is initially very high and it rapidly decreases. So therefore you have 3 components: the absorption current, the conduction current, and the capacitive charging current. These are in different time scales. As you can see, the capacitance charging current is the current that flows at the earliest instance of time. And after that, DC current takes over, and over and above DC current, you will also have the absorption current. And the total current beyond 1 second will be a combination of all 3 currents taken together. So that means this gives us an indication of what to expect from an insulation at different points of time. And this also gives us the idea that by making our measurements, we will be measuring current, measuring resistance. But because the currents will be changing with time, the resistance will also change with time. And by making resistance measurements at different points of time, we should be able to estimate values of the different processes. And because these different processes depend upon different material parameters and different physical processes, it will also give us an idea about the condition of the insulation. So let us quickly look at some of these tests that are important. So what we do is, we first do the short time test. The short time test is applied, so you apply voltage for 60 seconds. And this gives an indication of the insulation condition. So initially it is the capacitance charging current that flows, and the capacitive charging current will be determined by how good the insulation is. If you do not hold charge across it, it will not be able to charge fast enough and there will be leakage current. So the initial measurement will give us capacitance charging currents. So this is what we are looking at. This initial charging current is what we are looking at when we are making measurements, say up to 60 seconds. Then we have the time resistance test. The time resistance test is carried out for a period of 10 minutes or more. The insulation resistance is expected to settle down to a steady value by 10 minutes. But this is in the absence of moisture and dirt. If you have a lot of moisture or a lot of dirt, then the current may continue to fluctuate. When you carry out the time resistance test at 10 minutes or more, you are able to determine what is called the dielectric absorption ratio. What is this dielectric absorption ratio? The dielectric absorption ratio is defined as the 60-second value divided by the 30-second value. So if you look at this, by 30 seconds, you expect just capacitive charging current, whereas by 60 seconds, you are also looking at absorption current. The conduction current is of course there. So a ratio of the 60-second value and the 30-second value can give you an estimate of what is called the dielectric absorption ratio, which is how much absorption current there is and how much is the capacitive current. And if you take the 10-minute value divided by the 1-minute value, this is a measure of the polarization index, that is how much polarization takes place. If you have very large molecules, large polymers, it takes a longer time for the polarization current to settle down. So in both cases, these are kind of measurement of the slopes of these currents which rapidly go down to zero. Both of these currents, the absorption current and the capacitance charging current, are very high at the beginning and rapidly fall to zero. And the slope of these plots can be obtained from these ratios, and these ratios are defined as a dielectric absorption ratio and the polarization index. Now, from our experience, we have some idea about what kind of values we should expect in a good insulation. For a good insulation, you would expect a dielectric absorption ratio which is greater than 1.4 to 1.5, and you would expect a polarization index which is greater than 2. That means there is rapid fall in the current. Lastly, you have what is called the step voltage test. The step voltage test might be performed at 2 voltage levels, and these voltage levels can be very different. So maybe 1:5 ratio. So if you perform the first test at voltage V, the second test must be performed at voltage 5V. And at these values, you measure the resistance. If the insulation resistance value at the higher voltage is less than 75% of that at the lower voltage, then the insulation is suspect. Now, generally, if you apply higher voltage, the insulation resistance should not drastically reduce. If it drastically reduces, it means that it is conducting a greater proportion of current, which means that there must be certain things that are happening which cannot be attributed to simple conduction. It may be that you have partial discharges, you may have some defects which are causing very high losses. So if your insulation resistance falls rapidly with the increase in voltage, it is indicative of something wrong in the insulation. So these are in brief the 3 different kinds of tests that you can perform with a megger, where you do nothing but measure the resistance of the insulation system. Remember, we are not necessarily measuring just the resistance of a sample of a material, but we are looking at the resistance of an insulation system. Next, we come to the dielectric dissipation factor. The dielectric dissipation factor we have discussed very briefly in the introductory lecture to this course. This dielectric dissipation factor is also called the loss tangent, or the dielectric loss angle, or the DLA, and this is the easiest test which is used. the primary test for diagnosing possible degradation and deterioration of equipment installation, especially in the field. So in the factory, in the laboratory, on-site measurements, as soon as you measure the loss tangent, you get an idea about the bulk losses in the system. Remember, this gives a measure of the bulk losses produced under AC condition. And it enables changes in capacitance to be recorded and can be applied either at operating voltages or at prescribed test voltages, which may be much higher. So you can have an estimate of the losses in the system under AC operating conditions. And most often, we are not really interested in the absolute value, but we are interested in the trend. So let's say we have an equipment, we have an insulation system, and we keep measuring the dielectric dissipation factor. And if you see a sudden change in the dissipation factor, sometimes what we see is the dissipation factor reducing, the loss is increasing. Maybe it stays steady for some time and then it is slowly increasing, and then you see a sudden increase where you can see a sudden knee in the plot. So there is a sudden change in the slope of the loss with voltage, in which case you would suspect that there is something wrong and you need to take corrective action. To measure the dielectric dissipation factor, the simplest and the equipment that has been used for decades is the Schering bridge. This is the most common equipment that is used. It's a bridge circuit. You have a standard capacitor Cn, which is gas filled, has a nearly negligible loss over a wide frequency range. And then you have R4 and a adjustable capacitance C4, you have an adjustable resistance R3, and RxCx is your test specimen. The test specimen can be modeled as a series circuit consisting of a resistance and a capacitance in series. The resistance indicates the dielectric loss, the conductive loss of the circuit and of the test specimen, and the leakage of the specimen, and Cx is of course the capacitance of the specimen. So the arm RxCx has the test object and you have a galvanometer. And you need to obtain the balance conditions. Balance conditions are obtained when you have a balance situation between the arms of the bridges. So ZAB by ZBC should be equal to ZSC by ZDC. What is ZAB? ZAB is this capacitor. So therefore minus J1 by omega Cn. ZAC is Rx minus J1 by omega Cx. ZBC has the parallel combination of R4 and C4, which is R4 minus J1 by omega C4, R4 minus J1 by omega C4. And of course, Z3 is R3. ZDC is R3. So at balance condition, you have this scenario. As a result, what you can do is you can separate out the real and imaginary parts of the equation. So you have an equation here, and this equation, take out the real parts, equate with the real parts here, equate the imaginary parts, equating the real parts, you get Cx is equal to Cn into R4 by R3, and Rx is equal to R3 C4 by Cn. You can also obtain as tan delta x to be equal to omega Cx Rx, which is again equal to omega C4 R4. Now you may note that this tan delta quantity is dependent upon the frequency of measurement. Schering bridge is most often used in power frequency supplies, so omega can be considered to be 50 Hertz, but we can also have high frequency Schering bridges. So this is a very simple way of loss measurement or estimating the capacitive component and the resistive component of the test circuit. We also have a small variation of this in the sense that there are Schering bridges which work at ordinary voltages, Schering bridges which also work at high voltages. In a high voltage Schering bridge, you would generally have two RC arms with a sensitive electronic detector instead of having a vibrating galvanometer, and this electronic detector will be tuned to the test frequency. You choose which frequency you want to make measurements. It depends upon what frequencies, what kind of losses you are interested in, at what frequencies you want to measure the losses. We will discuss the issue of loss versus frequency a little later, but depending upon the frequency of measurements, the electronic detector will be tuned and you will have two RC arms. The dielectric dissipation factor values for more traditional insulating materials are in the range of 0.001 to 0.0003, and these are measurable by normal shearing bridges. But nowadays, we are more likely to use polymer materials, newer materials like XLP, cross-linked polyethylene, or polypropylene films, and these have much smaller DDF in the first place. So we are looking to measure DDF values less than 0.001, and these may not be measurable with a normal shearing bridge, and we have to look elsewhere. Another variation of the shearing bridge is the transformer ratio arm bridge. In this case, what we have is we have a 3-winding transformer. This transformer has very low losses and leakages. It has a high permeability coil, and it should be well insulated from stray magnetic fields. In this transform ratio arm bridge, we try to obtain the balance condition. The balance condition is obtained by changing the turns ratio of these two windings, N1 and N2. So you have a standard capacitor, Cn, just as you have in a high voltage shearing bridge. You have a Cn standard capacitor. You have the test specimen, which is given by Rx and Cx, and here you have the two turns ratio from the transformer, and you can adjust both 1 and 2 as well as C and R. So when you obtain the balance condition, at ampere turn balance, I1 N1 must be equal to I2 N2, and you can adjust R and C such that the phase shift Ix can be balanced. The phase shift in Ix can balance the losses in the test object Cx. So when, let's say you have an ungrounded test object, and if you neglect the impedances of the coils 1 and 2, assume an applied voltage of V, at balance you would have this condition: In is equal to V j omega Cn 1 plus j omega Cr divided by 1 plus j omega C plus Cn into R. Now this is the current that is flowing through the standard capacitor. Now, once it reaches here, it will divide into two branches, I1 and I2, and we can estimate these two quantities. I1 is given by V j omega Cx divided by 1 plus j omega Cx Rx, and I2 is given by In divided by 1 plus j omega Cr, which may also be written as V j omega Cn 1 plus j omega C plus Cn R. So, in terms of C and Cn and R, we do obtain the condition values of I1 and I2. I1 is of course dependent on Cx Rx. Now at balance condition, I1 N1 must be equal to I2 N2, and therefore equating these two equations after multiplying by N1 and N2 and equating the real and complex quantities, we can get an estimate for Cx of the test specimen, which is given by Cn into N2 by N1, and tan delta is obtained by omega R into C plus Cn. Now, if you look at this expression for the tan delta, we have Cn here. Cn is the standard capacitor. It is usually a gas type. For example, you might be using SF6, and this must be a capacitor which has insignificant losses for itself. At full voltage, it should not have very significant losses, because we want to only measure the losses which happen in the test specimen. So at full voltage, this can have a capacitance of the order of 100 picofarads. Remember, because of the very low impedance of the windings, the transformer windings, with this instrument, it is possible to make measurements with very high capacitances. So we can measure even up to 2000 picofarads with in one test. We may be able to measure with this kind of equipment.